Hello everyone, welcome to the lecture of IDS versus VDS in the MOS transistor. IDS is current from drain to source in MOS transistor and VDS is voltage from drain to source in the MOS transistor. In the last class we have seen the operation of MOS transistor, of the enhancement, depletion of the type of nMoS and PMOS transistors. In this lecture we are going to see the derivation of current, that is IDS, in the nMoS transistor and PMOS transistor of all the enhancement depletion types. Objective of this lecture is, you are going to model the current equation, that is IDS equation, in three regions of cutoff, non-saturation and saturation regions. After learning this, you will be able to derive the current equation for both nMoS and PMOS transistors of the type of enhancement and depletion. The contents of this lecture are a recap of the previous lecture and IDS derivation, then summary, and it follows the quiz and assignment questions. The summary of the last lecture, that is nMoS transistor operation. Here, by applying the VGS and VDS potentials, two potentials, we have seen different regions of operations. First one is by taking these two are zeros and VGS less than VTH, we have seen cutoff region, that means no current, no channel. And by increasing slightly this VGS greater than VTH, and by varying VDS values, non-saturation, saturation regions operation we have seen. So just it is VDS greater than 0, so for small positive value, that is VGS minus VTH, VDS less than VGS minus VTH, then channel is formed already because of VGS greater than VTH and electrons will flow because of the channel is there. That is the non-saturation region. And saturation starts at VDS is equal to VGS minus VT. Then similarly pinch off also starts and that pinch off existing, still it is continuing, and this is nothing but for the larger values of VDS. So these two are representing saturation regions. Still in the saturation regions, even the channel is pinched off, current is flowing, that current is constant and this is equal to maximum. And in this non-saturation region, current is existing and it is varying, that is, it is a function of VGS and VDS, both values. In the saturation region, current is function of only VGS, that is, it is independent of VDS in the saturation region. All these things we have seen in the last lecture. Now we are going to derive this I equation in the non-saturation region and saturation region in terms of VGS and VDS values. And whereas in cutoff region, how much is current? Since there is no channel, no conduction, current is equal to 0. So we are going to derive these current equations in the following slides. Start with the derivation, that is IDS, current. For this, let us take the 3D model of our nMoS transistor. So assume this is nMoS transistor and substrate is P-type and it is a source part, it is a drain part and this is the gate part. In the structure, we are going to have oxide layer. So this is SiO2. Here, dimensions are important to derive the current dimensions. The length of the gate or length of the channel. Length of the gate or length of the channel are same and these are representing, this is representing as L, capital L, and width of the channel is representing as W. This is width of the gate or width of the channel. Width of the channel, both are same here, that is representing with W, and For this oxide, thickness is there, that is represented with D, that is oxide thickness. Oxide thickness is represented with D. So dimensions important are, one is the length of the channel, width of the channel, and height of the oxide or oxide thickness it is called as. By taking all these into the consideration, we are going to derive the IDS equation. So IDS, since in the nMoS transistor, carriers are moving from source to the drain, that is electrons are moving from the source to drain direction. Therefore, IDS will flow, that is current will flow in the opposite direction of the electrons, that is from drain to the source. Therefore, it is representing as IDS. So, IDS, or this can be represented as inverse of source to drain. Therefore, minus IST, as the formula for the current is equal to channel by the time. Charge of the channel by the time. So, charge induced in the channel by transit time of the electron, it is representing as tau. So, I is equal to, we know the formula, that is rate of change of charge with respect to time. So, this is the I formula we know. Based on this formula only it is written, that is where here Q is equal to charge. So, charge induced in the channel by time change is equal to electron transit time. Here the electron is taking time to travel from source to the drain. So, these two are representing as channel charge and electron transit time, that is equal to tau. If we find these two, we can calculate the IST equation. Here, since I is equal to charge in the channel by tau, and actually it is representing as tau ST, because electron is travelling from source to the drain, tau ST, and in the non-saturation region or in the saturation region, channel charge differs, but channel electron transit time in the channel is same. The correct I is equal to QC by tau ST, where QC is representation of charge and tau is representation of the electron transit time. Here, the electron transit time tau ST is same in the saturation and non-saturation regions, that is tau ST is same. Why? Because the length of the channel is same in the both saturation and non-saturation regions. So, this is the channel shape in the non-saturation region and it is the saturation region. See, electron is transmitting from source to drain always. So, this much length it has to travel. Here also this much length it has to travel. Even though the channel charge and channel shape changed, here channel, this is the channel shape and this is the channel charge. And here this is the channel shape and that much is the channel charge. So, even though these two are changed, tau is taking off the time to travel the electron from this point to this point. So, therefore, tau is same in the both regions. So, tau SD is same in both non-saturation region and saturation regions. Whereas, Q is different, QC is different in both saturation and non-saturation regions. So, let us find first tau ST, then QC. So, therefore, we can find out the I is equal to QC by tau ST. Let us see tau definition, that is electron transit time tau is equal to length of the channel by velocity. This is actually written from the equation of velocity is equal to displacement by time. Here the displacement is equal to, in our channel this is equal to L, and tau is equal to, we have to find that as we have taken that as a tau, and this is the velocity of the electron. If you know velocity of electron and the channel length, then we can count simply tau. So, from this we have written as tau ST. Tau ST is equal to length of the channel divided by velocity. Now, velocity is equal to, velocity can be calculated by using the formula of velocity is equal to velocity depending upon the mobility of the carriers. So therefore, velocity is equal to mu into EDS, where EDS is applied electric field. That applied electric field depending upon the applied voltage. So that EDS is equal to VDS by L. Now by substituting this EDS in the velocity equation and by substituting that velocity equation in the tau equation, we will get as tau st is equal to this. So first substitute EDS in velocity, then velocity is becoming as mu into VDS by L, and now substitute this mu into VDS by L in this velocity equation. So that is equal to L square by mu into VDS. Now let's take simple equations, current equations. So let's take ISD definition, let's take IDS definition as equation 1, that is equal to QC by tau, and let's take the second equation as tau st, that is length of the channel by velocity. So final expression for the tau st is equal to, let us take third equation, tau st is equal to L square by mu into VDS. Now in our IDS equation, IDS is equal to QC by tau st. So this tau st part is ready with the equation 3. Now we have to find this channel charge. For this tau st, what is the conclusion? Electron transit time is directly proportional to L square, that is length of the channel, and inversely proportional to mobility and applied potential at the drain. So means tau is large when channel length is large. Means for the longer channel devices, electron transit time is more. Now let's see the charge expression. We have seen already charge is different in different regions. First, in cutoff region, since VGS is less than VTN, there is no channel means no charge. So there is no charge, therefore current is equal to 0. In other regions, that means in both non-saturation and saturation regions, in other regions, the gate attract the carriers because VGS we have applied as greater than of VTN. That gate attracts the carriers, that is electrons, from the channel. The electrons drift from the source to the drain at a rate proportional to the electric field between these regions. Therefore, we can compute the currents if we know amount of charge in the channel and at a rate which it flows. So, for finding of the charge, we are finding the charge. In the saturation, non-saturation it is different. In cutoff it is 0. For the saturation and non-saturation, first let's start with the non-saturation region. Let's see charge. Calculate the charge. Charge is different in both the non-saturation and saturation regions. So first find charge in non-saturation region. For this, charge formula is simply Q is equal to C into V. Q is equal to C into V. And our gate structure is look like of parallel plate capacitor. So this is the oxide, this is the gate part, and this is the channel part. So it is look like of parallel plate capacitor. So this capacitor, if you know this capacitance, we can calculate simply charge. So using that capacitance, we are going to calculate the charge. Q is equal to C into V. That is, Q is equal to Cg, that is the gate capacitance, into voltage, that is effective gate voltage, VGC minus VTN. Effective gate voltage means it is the amount of voltage attracting charge to the channel beyond the threshold voltage. Means till the threshold voltage point, the carriers are not attracting towards the surface or towards the channel. So it is a voltage beyond that, beyond the threshold voltage, which is attracting the carriers is nothing but Cg value. Sorry, VGC minus VTN value voltage. That voltage into Cg will calculate the charge. To calculate this VGC value, that is gate to the channel potential, gate potential and channel potential. How can write that VGC? VGC is equal to VG minus VC. VG is the gate potential and VC is the channel potential. To find the channel potential, what we are taking is, channel is nothing but between the source and drain. So this is the source part and this is the drain part. Now at the source already Vs potential is there, at the drain Vd potential is there in the channel. So Vs and Vd, so therefore the channel potential here we are taking as average of Vs plus Vd by 2. Now let's do a simple manipulation and calculation for that Vc to get in terms of Vds potential. That is, by adding and subtracting Vs extra, Vs plus Vds by 2 is the Vc potential. Now substitute that in the VGC expression, that is Vg minus Vc. So Vg minus Vc, Vc is substituted this. If we substituted that, Vgs minus Vds by 2 is equal to VGC, we got. So get to channel potential is equal to Vgs minus Vds by 2. From this equation we can tell the channel depends on both voltages. What we have seen in the yesterday's lecture, that is in operation, channel is first creating based on the potential applying at the gate based on the VGS. So this channel part is depending upon the VGS and the charge present in this channel depending upon the VDS value. After applying the VDS only, the channel charge is differed like this. So on average, the gate to channel potential is equal to VGS minus VDS by 2. Because here VGS is constant but VDS is variable. For that variable here, by taking off the average of that variable VDS by 2, we can get this also. So VGC is equal to VGS minus VDS by 2. Now VGC we have, let's find QC. QC is equal to, what is the formula? QC is equal to Cg into VGC minus Vtn. This is the equation. We have calculated VGC and Vtn is fixed value. So first we have to find the Cg. Cg is gate capacitance. It looks like parallel plate capacitance. For a parallel plate capacitance, the formula is C is equal to epsilon into area by D, where A is the area of the plates, D is the distance between the plates and epsilon is permittivities. So here this epsilon we are going to write as epsilon insulator and epsilon naught relative permittivity and free space permittivity, and then area of the gate. So what is the area of the gate? In this structure, in the initial structure we have seen the gate is like this, which is having of length L and which is having of width W, which is having of width W. So what is the area of the gate? Area of the gate is equal to L into W. So this A is equal to A is nothing but W into L. Then distance between the plates. Distance between the plates means already we have seen there is oxide in between gate and channel. So the gate and channel is separated with oxide. This oxide is having the thickness of D, means height of the oxide. So that oxide height or thickness of D is representing the separation gap between two plates. So therefore D is nothing but this capital D. So by taking off the formula of parallel plate capacitance, if we write the equivalent from our nMoS transistor, then it is equal to the gate capacitance. So gate capacitance Cg is equal to this. Now we are substituting that Cg value in the Q channel formula, that is what we have written earlierly. So Cg is substituting this and VGC, that is equal to VGS minus VDS by 2 by substituting that, and minus Vtn, we can get the value of QC. So QC in the non-saturation region is W into L into epsilon insulator epsilon naught by D into VGS minus Vtn minus VDS by 2. This is the QC equation. Let's take this as the equation 4. Now, substitute this equation 4 and equation 3, which we got as electron transit time, in equation 1, that is the current equation, so that we will get current derivation. So, equation 1 is equal to equation 4 charge divided by equation 3, that is equal to time. That is, IDS is equal to QC by tau Sd. QC is equal to, already we have seen QC is equal to epsilon naught epsilon insulator. In the previous slide we have seen QC is equal to this, and tau Sd is equal to L square by mu into Vds. By substituting this equation 3 and equation 4, we will get the equation as IDS is equal to this. IDS is equal to, this is the equation by substituting equation 4 and equation 3. This is equal to IDS, whereas here we are representing as some constant as K by taking off epsilon naught epsilon insulator mu by D, because all these are constants once transistor is fabricated. So simply this is equal to taking as K and now substituting this as K, the equation is rewritten like this. So let us take equation 5 it is. Equation 5 can be rewritten by taking K is equal to some constant value. So K into W by L into Vgs minus Vt into Vds minus Vds square by 2. And let us take this as the equation 6. Now, once the transistor is fabricated, W and L are also constant. So, let us take again the constant as beta, that is K into W by L. Now, substitute instead of these two as a beta, then the current equation is becoming as IDS is equal to beta into Vgs minus Vt into Vds minus Vds square by 2. So, we can simply remember beta into something, whereas beta is equal to K into W by L, where K is equal to this value. So, represent equation, this as the 7. Equation 5, 6 and 7 all are same, but with alternative representations. And this beta, these constants can also be represented in another forms, like in terms of gate capacitance and capacitance per unit area. So, gate capacitance is equal to formula already we have seen, and we are writing constant K in terms of Cg like this. What is the K value? In the previous slide we have written K value. So, K value is equal to epsilon insulator, epsilon naught by D into mu. So, K is equal to epsilon naught, epsilon insulator, mu by D is the K value. Now, I can write this K as Cg, because Cg is equal to epsilon insulator, epsilon naught, W by W into L by D. In this, I have epsilon naught, epsilon insulator D, but WL is not there. So, that's why just multiply and divide with W by W into L here. So, by making that, it will become as K is equal to Cg into mu by WL. Now, if I substitute that K in terms of Cg mu WL, then simply it is becoming as IDS is equal to Cg mu by L square into the equation. So, let us take this equation as 8, just rewriting of the equation. Now, we know capacitance C0 is equal to unit gate capacitance per area, that is Cg by area. So, that is Cg by W into L. If we substitute Cg is equal to C0 into WL, that is this. So, if we substitute Cg is equal to C0 into WL in the equation 8, we can get that in terms of C0. So, all these equations can be helpful while solving the problems, because in your exams you can get problems based on the current equations, but they will give some data. The data may be either C0 value or Cg value or these all individual constants values. If directly C0 is given, then you can use this formula, or Cg is given, you can use this formula. So, for that reason we are rewriting these many forms of the current equation. So, now how many ways we have seen? from the equation 5 to all equations we have represented. This is individual coefficients and all the constants values, and then equation 6 is representing in terms of k, and equation 7 is representing in terms of beta as a constant values, and remaining right part, that is voltage part, is same. There is no change in the voltage part. Then it is represented in CG form and it is representing in C0 form. So all these are different representations of the currents. So finally, our current in the non-saturation region is this. Current in the non-saturation region is this. Now, let's find current in the saturation region. Already we have seen non-saturation region, let's find the current in the non-saturation region is equal to IDS is equal to remember simply and to pronounce it easily, this equation is better to remember, beta into Vgs minus Vt into Vds minus Vds square by 2. From this what we can say? IDS is function of Vgs and Vds both. It depends on both the values of Vgs and Vds, which we have seen in the operation part. Now let's calculate the same current in the saturation region. In the saturation region, transit time is same, only the charge differs. Now instead of finding a channel charge once again, if we substitute the saturation current equation, saturation region conditions of voltages in the current of non-saturation region, we can find directly the saturation region current. So saturation region begins at Vds is equal to Vgs minus Vt. So therefore, substitute this Vds is equal to Vgs minus Vt in the above expressions. So those expressions, if I substitute Vds is equal to Vgs minus Vt, what is the equation of the non-sat region? IDS is equal to beta into Vgs minus Vt into Vds minus Vds square by 2. This is the non-sat region equation current. Now substitute Vds is equal to Vgs minus Vt in this. So if I substitute, this is equal to beta into Vgs minus Vt whole square minus Vgs minus Vt whole square by 2. This is the resultant one. So if I take a common of Vgs minus Vt whole square, then 1 minus 1 by 2, that will become as 1 by 2. So Vgs minus Vt whole square by 2 is equal to IDS in the saturation region. So that is written here. So those equations are written in terms of beta, in terms of Cg, in terms of C0 and in terms of K into WL. And still if we want, we can write as epsilon naught epsilon r mu by d into W by L into Vgs minus Vt whole square by 2. All these are the current equations in the saturation region. So what is the number in the last equation? Number 9. So we can represent as equation 10, equation 11, equation 12 and equation 13 for the representation of current in the saturation region. We can represent one more form, that is IDS is equal to beta. Substitute just this beta. Beta is equal to what? K into W by L. K is what? Epsilon naught, epsilon insulator, mu by D into W by L into Vgs minus Vt whole square by 2. This is IDS in the sat. So let us take this equation as equation 14. Equation 14. So all these equations will represent the current in the saturation region. Now we have derived the current equations of saturation and non-saturation regions. For the depletion transistor, what are the current equations? We have derived till now for the enhancement transistor current equations. For the depletion transistors, what are the current equations? For the depletion transistor also, the current is same, operation is same, voltages required are same, only the change is physical channel exists. Therefore, for this, the threshold voltage is negative. Threshold voltage for the depletion mode transistor of the nMoS type is negative. That is, VTD is negative, except that change all are same. Whenever we want to substitute in that equations, instead of VTN, we have to write the VTD in all the above equations, so that those equations will give the depletion mode nMoS transistor current equations. Let us see the current equations as a graphical representation for the both enhancement and depletion mode transistors. For the enhancement mode transistor, when VGS is equal to 0, there is no current, that is cutoff region, that is representing here. And then VGS is equal to increasing, VGS is equal to 0.2 VDD, 0.4 VDD, 0.5 VDD, 0.8 VDD, where VDD is power supply. So by increasing of VGS, current magnitude is increasing, and here this is representing the region of difference of non-saturation and saturation. And in the non-saturation region, these current equations are, our current graph is function of both VDS and VGS. Therefore, this is the representation of the VGS curve, and this value from this to this is representing the value of the VDS. So, it is function of both values. But in the saturation, even though VDS is increased, there is no change in the magnitude of the current, and it depending upon the VGS. So, VGS for 0.2 it is the value, for 0.4 it is the value, for 0.5 it is the value, like that. So, in the saturation region, the current is only function of VGS. That we have seen already in the equation. That equation defines, this is VGS minus VT whole square. That is, there is no VDS in the equation at all. That representation of the current for the enhancement transistor. Same for the depletion transistor. What is the change? Change is nothing but, for VGS is equal to 0, there will be some current. Then if you want to increase that current, we have to apply the positive potential, and if you want to decrease, we have to apply the negative potential. So for VGS is equal to 0, there is some current. This is the current graph representing when VGS is equal to 0, and VGS is equal to 0.3 it is representing, and minus 0.1 it is representing. The magnitude of current is lesser for minus 0.1 VDD when compared to the 0 and 0.3 VDD. So initial conduction is this. If you want to increase conduction, we have to increase VGS as a positive VDDs, and if you want to decrease, we have to apply negative voltage at the gate potential. This is only the difference. Current equations are same. Here same relation follows. Here it is a function of both VGS and VDS, and in the saturation it is function of only VGS, not the VDS. Same equations. So this is the explanation of those current equations in terms of graphs. Let's summarize the equation part for the nMoS transistor of the enhancement type, region of operation, then characteristic equation of the current, and VGS and VDS values. Cutoff region, what are the conditions? We know already. VGS is less than VTH and VDS is equal to 0 value. There is no VDS, or even though there is VDS, because of the VGS is less than VTH, the current is 0 because of the absence of the channel. Then linear mode or non-saturation mode, the voltages VGS should be greater than VTH and VDS is less than VGS minus VTH. Then current will follow the equation of this, that is beta into VGS minus VT minus VDS by 2 into VDS. Then in the saturation region, VGS should be greater than VTH and VDS should be greater than or equal to VGS minus VTH. Then the current equation is beta into VGS minus VT whole square by 2. See here from this, the current in the non-saturation region is function of both VGS and VDS, whereas in saturation region it is just function of VGS only. Whereas VTN is constant or VTH is constant and all others are constants only. Mu, N, C, W, L all are constants only. So these are the current equations we have derived in the nMoS transistor enhancement mode. Same equations are applicable for the PMOS transistor also, where just polarities of the voltages are reversed. See here, in nMoS if we have taken IDS, then in the PMOS it is becoming as source to drain current, that is IST. And VGS we have taken here, then VSG it will become, then VDS is becoming as VST, means opposite polarities they are becoming, opposite polarities. VTH is becoming of minus VTH, VDS is equal to minus VDS is representing as VSD only. Like that the polarities are becoming as negative in the PMOS transistor. By applying just those negative polarities in the above equations which we have derived in the nMoS, those are equal for the PMOS transistor equations. So directly I am showing here as a PMOS transistor equation part. The region of operation is 3 regions: cutoff, non-saturation and saturation. Similarly, the voltage ranges for defining the cutoff, non-saturation and saturation regions, which we have seen already. And then cutoff region, anyway, that may be a PMOS or nMoS, the current is 0. The current is 0. Here see, current is representing as IST. And in the linear mode, that is in the non-saturation mode, just substitute the equation. What is the IDS in the nMoS? That is mu n into COX into W by L into VGS minus VTN minus VDS by 2 into VDS. This is the equation for the nMoS. Now here just replace, instead of mu n, mu p, COX is same, WL are same. Then VGS, instead of VGS what we have to substitute? VSG. So here let us take VSG minus VTN is nothing but VTP. So that VTP is negative. So minus of minus is becoming as positive. So VSG plus VTH minus VDS. Instead of VDS what we have to take? VSD. So take VSD by 2 into VSD. This is COX into W by L. So this is equal to the current equation in the PMOS transistor, where that is representing here. ISD is equal to mu P into COX W by L, VSG plus VTH minus VSD by 2 into VSD. So like this, by substituting these parameters in the nMoS transistor equations, you can find directly, you can write directly the PMOS transistor current equations. Similarly, the saturation region PMOS transistor equation also follows. So therefore that equation is half mu P COX W by L into VSG plus VTH. There we found as a minus, but here it is plus because VTH is negative. So these are the current equations for the PMOS transistor if we directly apply the polarities. If you don't want to apply the polarities in the PMOS, if you want to take only the absolute values, then we can take the absolute values. So therefore the equations are becoming like this. Absolute means we are taking the magnitude of VGS, magnitude of VDS. Instead of taking a negative polarity directly, if you are applying the magnitudes, then equations are as it is same as the nMoS with magnitude substitution. See, in the cutoff, magnitude of IDS is 0. Magnitude of IDS is equal to actually IST. IST and is IDS both are reverse. IDS is equal to minus IST actually. But we can write this as magnitude of IST is equal to IDS. So therefore, we have written directly, instead of taking the IST and minus IDS, directly magnitude of IDS. So magnitude of IDS is equal to 0. Same. Mu P COX here, magnitude of VGS. Instead of taking the VSG, magnitude of VGS. Like that. If we take the all absolute values, these equations are exactly look like nMoS transistor values, nMoS transistor equations, just by replacing the magnitude values only. So you can use either absolute values part or actual values equations Depending upon your choice or depending upon the given values in the problem, we can use any one of these equations. So this is the equation part, current equations for the PMOS enhancement mode transistor. Now if you want to get the PMOS depletion mode transistor equations, just it is replace of VTH in terms of positive value. Here for the enhancement mode PMOS, the threshold value is negative. So therefore depletion mode PMOS threshold value is positive. So just substitute that positive so that these equations will become as depletion mode transistor equations. So till now we have seen the current equations for nMoS enhancement, nMoS depletion, PMOS enhancement and PMOS depletion transistors. Now let's have this small quiz to check our understanding of those derivations and current equations. First one, IDS can be given by, what is the current equation definition? First we have written, that is channel charge by the transit time. So therefore IDS is equal to, from the given options, channel charge QC into T, it is not, and QC by tau, okay, tau by QC is not, and QC by 2 tau T is also not. So the option is QC by tau, current is equal to charge divided by time. And IDS is dash to length L of the channel. So IDS, how the IDS is proportional to the length? What is the equation? IDS is equal to beta into something or K into W by L into the voltages part. So from this we can see IDS is inversely proportional to the length. So from the options, what is it? IDS is inversely proportional to the length value of the channel. Then let's see this. IDS is independent of VDS in saturation region, whether it is true or false. IDS is independent of VDS. Yes, because already we have seen the graphical part and equation part both. After non-saturation region, in the saturation region, even though VDS is increased, IDS is constant. So this is the constant representation. So IDS is independent of VDS. So independent of the VDS, it is equal to true. Then electron transit time is dash to length of the channel. Electron transit time is what? Tau, tau Sd. What is the equation for tau Sd? Tau Sd is equal to L square by mu into VDS. This is the equation which we have seen. So this is directly proportional to L square, inversely proportional to mu into VDS. So what is the question asked? That is equal to the relation with respect to the length L. So length is directly proportional. So out of the given options, length is directly proportional. So these are the questions which are testing us for the understanding of these. So if you answer these, it is okay. Take these as assignment questions. Derive the IDS equations for PMOS transistor, because in the derivation I have derived nMoS transistor completely and rewritten the nMoS equations as for the PMOS to get the PMOS. So therefore directly derive IDS by taking the charge calculation, tau calculation and etc. Derive the equations for PMOS. And then let's do this. It is a sum actually. Solve this, and if you have doubt, ask me. Follow these two textbooks. Mainly I have taken this content from the Bucknell textbook and Western textbook. So follow these two textbooks for this derivation part. What we have seen till now, the summary part, that is the current equations, modeling of the current or deriving the current in both nMoS transistors and PMOS transistors. That too in the nMoS transistor of enhancement we have seen, and depletion also we have seen. And similarly in the PMOS also, PMOS also enhancement type and depletion type. For the 4 types of the transistors, modeling of these IDS equations we have done. So in this lecture we have seen IDS calculations. We will see the parameters, different parameters of the MOS transistors in the next lecture. Thank you.